Welcome to Center of Mass. So the general idea here is we'll be looking at two-dimensional objects, or we'll be looking at technically thin flat plates. Of uniform density. Whose shape is given by a region in the 2D plane. So by a region in the XY plane. So for example, we may have some region that's bounded above by f of x and below by g of x, and then bounded on the sides by x equals a and x equals b. The center of mass is essentially, if this were a really flat plate, it's the point where you could balance the entire plate at that one point. So the center of mass is the single point within the region where you could balance the plate on a pin or hanging from a string, however you want to see it. So the formula for finding center of mass, we will have a formula for the x coordinate and a formula for the y coordinate. So the formula for the y coordinate in some ways is actually easier. But essentially what we were going to do is to find the x and y coordinate. Or x and y coordinates. The first thing we need to know is just the mass of the object. So the first thing we need to know is find the mass of the plate. And since the object has uniform density, if we set the density equal to rho, Greek letter rho, then the mass is just rho times the area of the plate, which is simply rho times the definite integral from a to b of our top function is f of x, bottom is g of x. So f of x minus g of x dx. The next thing we need to do is find what are called the moments. So next up, we have to find the moments. The moments are essentially a measure of an object's tendency to rotate about the x and y axis. And the way that moments are found are we add up. So to find a moment, about an axis, we essentially take each bit of mass or each distance from the axis and multiply by the mass at that axis, mass at that distance, and then add it all up. So to find a moment about an axis, for each distance, from the axis, or displacement from the axis, I should say. For each displacement from the axis, find the mass at that displacement. From there, we multiply the displacement times the mass. I need to give myself a little more room. Again, we multiply each displacement times its mass. And then we add up all of those products. So this is actually easier to see the formula about the y-axis than it is about the x-axis. So let's first do the moment for the y-axis. So which we denote my equals the moment about the y-axis. If we draw our picture again, whatever shape we have, running from A to B, we can see that the displacement, if we take a slice of our mass or a slice of our object, right, the displacement from the y-axis is just x. So our displacement is x to that slice. The mass of that slice is just the density times the area. Our density is rho, and the area is the integral from, sorry, it's not the integral, it's just f of x minus g of x times dx. So again, our top function was f, our bottom function was g, and we ran from A to B. So if we want to then sum up all of these products, so summing up the products, we wind up getting that my is simply equal to the integral from A to B of, I apologize, my is equal to the integral from A to B of rho times f of x times, or f of x minus g of x times dx, and then times the displacement. That's kind of an awkward way to write this. Instead, we write this as putting that x back in front. We have, and the row really out front, we have rho as a constant. We can pull it in front of our integral. Then we have x times f of x minus g of x dx inside our integral. So again, we were supposed to take the product of displacement and mass. So we are taking the product of x times rho times f of x minus g of x dx, and then adding up those products. So we are looking at rho times the definite integral from a to b of x times f of x minus g of x dx. So this is the moment about the y-axis. The moment about the x-axis is a little less straightforward. So when we go to find the moment about the x-axis, again, draw the same shape we've been looking at. F is up top, G is down below, running from A to B. Once again, we are still going to look at a slice, a vertical slice instead of a horizontal slice. And this time around, essentially what we are going to do is we are going to imagine that the entire mass is actually at sort of the middle of that slice. So we are going to imagine all of that mass is located in the middle of the slice. Instead of spread out throughout. So the displacement will be from the middle down. So the displacement will essentially be the average of F and G. So it will be the average of f of x and g of x. Which is better known as f of x plus g of x over 2. And then the mass, we will find exactly how we found before. Once again, I need to give myself more room. I apologize. So the mass, again, is the exact same mass we had previously. So the mass will once again be rho times f of x minus g of x times dx. Then we take the product of these. So we take the product. And we are looking at rho. Well, we'll do the f of x plus g of x over 2 first. So we are looking at f of x plus g of x over 2 times rho times f of x minus g of x times dx. The f of x plus g of x and f of x minus g of x just multiply nicely together to make f of x squared minus g of x squared this whole thing is being multiplied by a rho over 2 and multiplied by dx. So from here, just like previously, we now have to sum up the products. So again, we were looking at slices, vertical slices. So we're still gonna do an integral from, we'll still do an integral from a to b. We're integrating with respect to x. Then we have rho over 2 times, we have f of x squared minus g of x squared, and then dx. And of course, that rho over 2 can be pulled out front. We have rho over 2 times the definite integral from a to b of f of x squared minus g of x squared all times dx. At this point, notice that if we are sort of measuring movement about the x-axis, we're actually looking at vertical displacement usually. Movement about the y-axis, we are looking at horizontal displacement. So it actually turns out when we go to calculate the center of mass coordinates that we will swap which one we use with what. So for our calculate the center of mass coordinates, to calculate the center of mass, our x mean is given by taking the moment about the y-axis, my, and dividing by our mass, which I'm going to call m. I don't remember if I actually labeled mass. So we're going to call mass m. I apologize for the scrolling. So we do my over m. This is rho times the definite integral from a to b of x times f of x minus g of x dx, all over rho times the definite integral from a to b of f of x minus g of x dx. Of course, the rows cancel. So we are essentially looking at the definite integral from a to b of x times f of x minus g of x dx, all over the area integral from a to b of f of x minus g of x dx. For our y coordinate, this is taking much more room than I expected. For our y coordinate, we are looking at mx over m. I'm just going to box our x coordinate quickly. So here is our formula for our x coordinate. And then for our y coordinate, let me give myself a little more room again. So for our y coordinate, we are looking at, again, the definite integral, rho over 2 times the definite integral from a to b of f of x squared minus g of x squared dx. And then all of that is over rho times the area, rho times the definite integral from a to b of f of x minus g of x dx. Once again, our rows cancel. So we essentially wind up with y bar is equal to 1/2 times the definite interval from a to b of f of x squared minus g of x squared dx, all over the definite interval from a to b of f of x minus g of x dx. Oh, sorry, I meant to box that, not cross it out. So for my class, you're welcome to jump straight to the formulas. So this is where the formulas come from. So this is where the formulas come from. For calculating the coordinates of the center of mass. You are welcome to jump straight to using the formulas. So I apologize for the slightly lengthy video, but we can go ahead and let's go ahead and just do one example. So let's find the center of mass for the shaded region, which is not actually shaded here. So the shaded region, which is bounded above by y equals square root x and below by y equals x cubed. So note the points of intersection are at 0 and 1 for our x values. So our area, our first integral of interest, we are looking at the integral from a to b of our upper equation is square root x minus our lower equation, x cubed, then dx. So we have our area is definite integral from 0 to 1, a and b are 0 and 1, of x to the 1/2 minus x cubed dx. X to the 1/2, of course, becomes 2/3 times x to the 3/2 when we integrate. And we have minus 1/4 times x to the 4th. And we are evaluating from 0 to 1. So this becomes 2/3 minus 1/4 minus 0. Or 8/12 minus 3/12 would be 5/12. This is our first integral of interest. Our second integral of interest is the integral from 0 to 1 of x times f of x minus g of x. So times the square root of x minus x cubed dx. What I'm finding right here is my over, actually, let's just jump straight to finding our x bar. So x bar, we take this integral and we divide by the area. So we are looking at the integral from 0 to 1 of x to the 3/2 minus x to the 4th all over 5/12, and I forgot my dx there. This becomes 12/5 times x to the 3/2 goes to 2/5 x to the 5/2. Then we have 1 minus 1/5 x to the 5th, and we are evaluating from 0 to 1. So we have 12/5 times, we have 2/5 minus 1/5, and then minus 0. 2/5 minus 1/5 is, of course, 1/5 times 12/5 gives us 12/25 for our x coordinate. For our y coordinate, we have our y coordinate as given by doing 1/2 the integral from 0 to 1 of f of x, which was square root of x, squared, minus g of x, which is x cubed, squared, dx, and then we divide again by the area. So we are looking at 1/2 times the definite integral from 0 to 1 of x minus x to the 6th dx, all divided by 5/12. This becomes 12/5 times 1/2 times x goes to 1/2 x squared minus x to the 6th goes to minus 1/7 x to the 7th, and we are evaluating from 0 to 1. This, of course, becomes 6/5 times 1/2 minus 1/7, and then minus 0 when we plug in 0. So we are looking at 6/5 times 1/2 minus 1/7 would be 7/14 minus 2/14, otherwise known as 5/14. And this simplifies. 6/5 times 5/14 becomes 3/7. So our center of mass occurs at the point, our first coordinate was 12/25, and our second coordinate was 3/7. So this is how we can go about finding center of mass for a plate with uniform density.